The first one is a well-known Putnam boy. Can you solve the second one? Okay. So for the first one, there is a well-known method and it's a popular integral. The way you solve is, first of all, you make a substitution x equals to tan theta. Yeah. And after that, you will see that this dx by 1 plus x square will just be d theta. Yeah. And after that, you have to make a clever use of King's rule. And then after use of King's rule, you will see that the integral will be solved in some ways. Okay, so you can search that in internet. I mean, in YouTube, this is already solved, or also in my own channel as well. But for this video, we are going to solve this integral, and the answer for this one is actually pi by 8 ln 2. Now let's go with another integral. How do we think we can simplify this one? We can basically do the integration by parts first of all, so that this gets differentiated and this gets integrated. That will somehow simplify the problem, yeah, because the term with the 1 plus x, now it's being taken to the ln, so that's simpler than the what is here now, right now. So if it's integration by parts with this as u and this as b, we basically get ln of 1 plus x square, and then the integral of this thing is ln of 1 plus x. Yeah, this is going from 0 to 1 minus integral from 0 to 1. Derivative of this expression is 2x by 1 plus x square. Yeah, and the integral of this is ln of 1 plus x and then dx. Now how do we proceed further? If we evaluate this at 1, this will just be ln square of 2 minus 0. Yeah, and over here this is minus 2 times integral from 0 to 1 x ln of 1 plus x by 1 plus x square dx. Okay, now what's next? What do you think the next step that we can take? To simplify ln, we can basically change it to an integral again, yeah, and then we will kind of have a double integral. So let's try to do that. That will simplify it. Ln square 2 minus 2 and then integral from 0 to 1 x by 1 plus x square, yeah, and then you have ln of 1 plus let's introduce y, and then y going from 0 to 1, yeah, and dx. Now in this way it basically evaluates to ln of 1 plus x itself, yeah, and then now we can change it to an integral by just differentiating this expression. We get ln square 2 minus 2 times integral from 0 to 1 x by 1 plus x square, and then the derivative is 1 integral from 0 to 1 and then 1 by 1 plus xy, and since we are differentiating with respect to y, we have to get the x over here as well, and so dy dx. Now we have a double integral. But do you think is it any way easier? Let's see. Now one of the techniques that we can use is to interchange the integrals. Yeah, if you interchange, you see that most of the time it simplifies. Yeah, and though it may not work always, but it works a lot of times, and that's what we are trying to do in this problem as well. Yeah, now let's try interchange the integrals. Yeah, what do we get then? We get ln square 2 minus 2 times, if we interchange the integrals from 0 to 1, from 0 to 1, x square by 1 plus x square 1 plus xy dy dx. Now we want to, okay, no, so I think because I have changed the order of integrals, this should be dx dy. Yeah, Now, how do we begin solving this problem? Basically, supposedly, like I'm basically now I will try to use the partial fractions way. And since this integral is in the world of x, I will basically consider y as a constant while making the partial fractions. Yeah. Then let's try to do that. Ln squared 2 minus 2 times integral from 0 to 1, integral from 0 to 1. Now if we try to use the partial fractions, what we get is, I basically already have done the partial fractions, so I don't think I'm gonna do it again. And let me show you what I have gotten. So if I basically do the partial fractions, what we get is this expression. Or shall we do? Shall we do it again? Yeah, I think let's do it. Let's not skip this person again. So if we try to do that once again, let me do it because it's fun to do. What we get? So basically, let me do it inside. Yeah. So we basically have x square by 1 plus x square 1 plus xy, and this is basically ax plus b by 1 plus x square, and then since here is just an x and a constant, so we just have a constant as well here, 1 plus xy. Yeah. And then we have now consider y as a constant throughout this manipulation. Okay, now we have x square is equals to ax plus b times 1 plus xy plus c times 1 plus x square. Yeah. And what's next? Okay, so if we try to compare the coefficient of x square, we will have ay plus c is equals to 1. Is it? Do we have ay plus c is equals to 1? Yeah, we have. Now if you try to compare the coefficient of x, we basically have over here a plus by, yeah, if we try to by, and then I think that it is equals to 0 because there is no x in over here. Try to compare the constants, we have b plus c is equals to 0. Is that it? Okay, so there are 1 2 3 5 6 terms. 1 2 3 4 5 6, yeah, 6 terms. I think that's going great. Now we know that b cost minus c, so we have a minus cy is equals to 0. That means a is equals to cy. Now what does that imply next? Since a is cy, we have cy square plus c is equals to 1. That means c equals to 1 by 1 plus y square. Yeah, 1 by 1 plus y square. And then since we have c as 1 by 1 plus y square, a will be y by 1 plus y square. Yeah. Now since a is y by 1 plus y square, we will have now we know that a is equals to cy. C is now b is just minus c, so b is equals to minus 1 by 1 plus y square. So we have now the coefficients and we are good to go, good to move ahead. So ln square 2 minus 2 times integral from 0 to 1, integral from 0 to 1. So first of all, our a is y by 1 plus y square. So y by 1 plus y square times x by 1 plus x square plus, now b is minus 1 minus 1 by 1 plus y square by 1 plus x square, then plus c is 1 by 1 plus y square by 1 plus xy, then dx dy. Yeah, okay. Now what can we do next? We have ln squared 2 minus 2 times integral from 0 to 1. Over here we have xy by 1 plus x square 1 plus y square, yeah, minus 1 by 1 plus x square 1 plus y square, and then plus 1 by 1 plus y square 1 plus xy, and then dx dy. Now over here there's a pretty good way to simplify this, but before moving ahead I would like to check my calculations till now, because I'm not really sure if I will do great. Okay, fine. Now after this it's going good. Till now. Yeah. After this, what do? We know that this is just symmetric about x and y. Yeah, so you can change it to single integral squared. Yeah. Ln squared 2 minus 2 times this is integral from 0 to 1 x by 1 plus x squared dx whole square, and then minus minus plus 2. This is integral from 0 to 1 by 1 plus x squared dx whole squared, and then again there is minus 2. Yeah, and now I would like to write this as because since this integral is symmetric about x and y, I can interchange the x and y, so this will also be equals to 1 plus x square by 1 plus xy. I would like to write this in this form, and there's a reason for doing it. The reason is, we know that this is also I, this is also I. Yeah. Now if I try to add these two i's, basically the first thing is ln square 2 will be added. Yeah? But here I will have 1 plus x square, because these two are the same almost same. Yeah, and denominator is same, so we can add the numerators, and there's cancellation after that, so that's a good thing. So if I add these two integrals, I basically have 2i equals to 2 times ln squared 2 minus 2 times, now this is 1 by 2 ln of 1 plus x square from 0 to 1 squared plus 2 times tan inverse x from 0 to 1 squared. Yeah, and then basically minus 2, and basically since the denominator is same, we have x square and 1 added to each other, so we have 1 plus x square by 1 plus x square 1 plus xy dx dy. Yeah. Now after this, what do we have? This cancels out. Yeah, and now this is an easy integral. Yeah, we can do that easily. I can basically change this to a geometric sum. Yeah, because we have a by 1 minus r form, and then do it. So we have now I is equals, I can take 2 here, ln squared 2 minus, so this is 1 by 2 ln 2. Yeah, the 2 cancels out, because this 2 will cancel all the 2's over here. Now this is ln 2 by 2. Yeah, if we value this, so we get ln squared 2 by 4, and we know that this is pi by 4, so pi square by 16, and now this is sum from integral from 0 to 1, then this is sum from n equals to basically 0 to infinity of x minus xy to the power n, yeah, and then dx dy, yeah. So I basically now have I equals to ln squared 2 minus, that means 3 ln squared 2 by 4 plus pi square by 16 minus, now basically these two are also same integrals with x and with y respectively, so I can write this as sum from any, I can interchange the sum and integrals, and then write this as minus 1 to the power n, basically integral from 1 to 0 to 1 of x to the power n dx, and then square this one, yeah. Now I think you are seeing where it leads us, yeah. So I is basically 3 ln square 2 by 4 plus pi square by 16 minus sum from n equals to 0 to infinity of minus 1 to the power n, and then this is just 1 by n plus 1 square, yeah. Yeah, okay, no, x to the power n plus 1 n plus 1, yeah, I think that's good enough. Now I think we are really at the close of this problem. Okay, so if I now try to take this, if you now try to see this sum, this sum is just like 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square. This is just eta function of 2. We know that eta function of s is just 1 minus 2 by 2 to the power s of zeta function of s. So that's why eta of 2 will also be 1 minus 2 by 2 square. So that's 1 minus 1 by 2. That's 1 by 2. 1 by 2 times zeta of 2 is pi square by 6. So this is pi square by 12. Yeah. And we get 3 ln square 2 by 4 plus pi square by 16 minus pi square by 12. Now if I write 1 by 16 minus 1 by 12 in the calculator, I get minus 1 by 48. So we have 3 ln square 2 by 4 plus, so pi square, and the LCM will basically be case 48 itself, yeah, and 16 times 3 minus 12 times 4. So answer is 3 ln square 2 by 4 minus pi square by 48. Now this is the answer because this is supposed to be the I, this is supposed to be the I, this is supposed to be the I, and this is the answer, 3 ln square by 2 by 4 minus pi square by 48. Yeah, write it over here, 3 ln square 2 by 4 minus pi square by 48. So I think that's the thing. Hope you enjoyed the solution. This was a really awesome solution. And if you have talk about the solution development, we used integration by parts, and then double integral, and then partial fractions, and then the observation, and the sum notation of symmetry series, an integral, and we got the answer. So this was it, and this was a wholesome journey. Hope you enjoyed the video. Thanks for watching, and look forward to seeing the upcoming videos too.